Now we will talk about another paradox, and this is probably one of the most frequently discussed in the debate between frequentist approach and Bayesian approach to the data analysis. And the name of this paradox is called Lindley's Paradox. And it is named after statistician Dennis Lindley, who coined this term paradox associated with this phenomena in the 50s. But the phenomena itself was described in Jeffries in the late 30s in his book. And the paradox talks about two different approaches to hypothesis testing. So the Bayesian approaches to hypothesis testing relies on the Bayes factor, and the frequentist approach relies on the p-value. And if you remember, the frequentist approach starts with formulating a null hypothesis. So we have a null hypothesis H0 stating that parameter theta that we don't know equal to some null value theta 0. And in frequentist approach, so this is a frequentist approach, the alternative hypothesis H1 is always complementary to the null hypothesis. So if H0, the null hypothesis, says equal, then the alternative hypothesis will say not equal. And the way we resolve and answer which hypothesis we need to accept, you remember we have to have enough of evidence against null hypothesis to reject it. So null hypothesis is the status quo, and the data needs to be devil's advocate and advocate against the status quo, the null hypothesis, in favor of H1, and evidence needs to be strong enough before we can say that we reject the null hypothesis. And the way you do it, right? So we applied to analyze the averages. So let's say you have some average. I'm gonna call it x bar n, and it's calculated from a data set. So it's just you take your observation and you average them out. And central limit theorem tells us that this average follows normal distribution, and normal distribution is centered is at theta. This is the value that comes from the hypothesis testing, and the variance is the variance of the original data divided by the n, where n is the size of the sample. And then we calculate the t-statistic. So t is just the distance between the calculated average and the value specified in the null hypothesis. And we measure this distance in standard deviations. So we divide by sigma divided by n squared. And we know that the t-statistic follows normal distribution, standard normal, 0, 1, under the null hypothesis. And then we basically compare the way we answer the question, whether we should accept alternative hypothesis or not, is we compute the p-value. So p-value given this statistic t, and it equals to probability that t, capital T, greater than the small t that we calculated, and it's just 1 minus phi t. So, and this one is the CDF of the standard normal. CDF of standard normal. Okay, so we basically calculate the area under the curve on the right of this number, and relying on the p-value, we basically determine whether we reject null hypothesis or we do not reject the null hypothesis. So that's the frequentist approach to the to the hypothesis testing. In the Bayes approach, relies on what is called Bayes factor. Remember, Bayes factor is the ratio of the likelihoods, and in this case, it's going to be ratio of the marginal likelihoods of two alternative hypotheses. So you have the null hypothesis, and let's say on the null hypothesis, your parameter theta, the prior is normal, so it follows normal distribution centered at some value theta 0 with variance sigma squared. And then let's say you have alternative hypothesis, which is uninformative prior, so it's uniform uninformative prior. And let's say that you start by assuming that both hypotheses are equally likely. So the probability that hypothesis 0 is true equal to the probability that hypothesis 1 is true and equals to 1/2. So those are your prior probabilities. You have prior probabilities on the hypothesis, and then you have prior probabilities on the theta under each of those hypotheses. And then you need to calculate this Bayes factor. Bayes factor is just the ratio of marginal likelihoods. So let's write down what Bayes factor is. So you have, first of all, we want to know the probability of hypothesis 0, the null hypothesis, given the data, given the value of x bar that we calculated, divided by the probability of the alternative hypothesis, given the data that was calculated. So that's what the Bayes factor is. And you remember, in order for us to calculate this, both of the parameters h0 and h1, they depend on this parameter theta, and theta in this case is random, so we have to integrate it out. And actually, if you do this integration and then you calculate the Bayes factor, then you will see that it equals to 1 plus n power 1/2, then exponent. We're not going to do the calculations here, just going to write it down, minus n, the t value that we calculated divided by 2, 1 plus n. Okay, so that's the Bayes factor. And then we say if our Bayes factor is greater than 1, then seems like that h0 is a better better hypothesis, meaning explains data better than hypothesis h1. Okay, and the Lindley paradox is that for certain values of t and n, what you will find out that on the frequentist approach, you would reject null hypothesis, and under the Bayesian approach, it will be vice versa. You will find that the Bayes factor shows that the null hypothesis is much more favored. It's a better explanation of the data set. And for example, when t equals to 1.96 and n equals to 16,000, H118, so this is backward calculated value, then the frequentist approach under 95% confidence says that theta is not equal to theta 0. However, under the Bayes approach, we are our belief is our belief is 95% chance that the true value of theta is actually equals to theta 0. So this contradiction is called the Lindley Paradox. And so that's the summary for the Lindley Paradox of an evidence which for Bayesian statisticians strikingly support the null leads to rejection by the standard classical procedures. And it shows that the Bayesian and the classical approaches do not agree. And again, Bayesian calculates the probability of the null being true given the data. That's not the p-value. And they do agree asymptotically, meaning that if you make the value of alpha go into 0 as n goes to infinity, then things work out actually. So you just have to make your lambda to be smaller and smaller as n goes to infinity, and then they will keep agreeing to each other. This has been a very heated discussion in the statistics community, and the most recent view on this and the Bayesian view was given by Christian Robert, and it was paper published in 2013. So actually, if you go to the Wikipedia page and you look for Lindley Paradox, this paper is referenced there. It's Liedman and Savage in their 1963 paper on applying statistics to psychology show that you actually can approximate the likelihood ratio. So, and this ratio is approximately square to pi, root n, and then exponent, and then you have t squared at the exponent. And what you see here is this root n term here. So the likelihood ratio is proportional to the root n. That means that as n goes up, your exponentially will favor the, or asymptotically will favor the null hypothesis. And let's look at the simple experiment. We have for experiment, we toss a fair coin, and n shows the number of the tosses, and r shows the number of favored outcomes, let's say tails. And in each of the cases, the ratio of n to r is roughly 2 to 1. And of course, the null hypothesis is that the coin is fair, and the alternative hypothesis, the coin is not fair. And you see, the more tosses you make, the more favored the null hypothesis looks like under the Bayes condition. In the classical case, in each case, the t ratio is approximately 2, and we reject null hypothesis, a fair coin, at the 5% level experiment. And under the Bayes modeling, the likelihood ratio grows to infinity, and so you overwhelmingly get evidence towards the null hypothesis H0. And Conley showed the same analysis applied to markets. There is something what is called the Monday effect. People believe that trend on Monday is the continuation of the trend on Friday, and if you use frequentist approach, that seems to be the case. However, under the Bayes version of the analysis, this Monday effect basically disappears.